Okay, we know what a definite integral is. It's a product of x and y. I'm going to use that with my unit analysis to figure out what a definite integral represents. But going back to that previous problem, is there a better way than counting blocks? I mean, that seems like a pretty slow way of estimating the value of a definite integral. So other geometric strategies that I could have used, other than counting blocks, was to look at the symmetry of that looking like a parabola. That's what I actually did. I only counted half of it. But what I could do is I could break that into smaller, recognizable shapes. I could draw a couple rectangles in there, maybe a few triangles, do my best to kind of puzzle piece that thing out so it looks like some shapes that I could easily find the area of. So how many shapes would I want to have in there? 1, 2, 3, 4, 5. How many shapes would be the best way to get the value of that definite integral? You're thinking a lot, aren't you? Whew, a lot. In fact, if I had an infinite number of little tiny shapes in there, that would give me the best approximation of the definite integral I could possibly get. In fact, it would be the value of the definite integral exactly. Stay tuned. We're going to get there. All right, so this is called a Riemann sum. A Riemann sum is simply the sum of the areas of familiar geometric shapes. Okay, missed a word in there. It's the sum of the areas of familiar geometric shapes. So we're a Riemann sum. That's what it is. What it does is it approximates the value of a definite integral. Okay, so it seems as though we're using these areas to find the value of a definite integral, which again confuses the uninitiated, because the uninitiated think that a definite integral is just area under a curve, but it's not. And that's kind of where some of the confusion lies, is that we're using area to get something that's not technically area, but it just looks like area. So stay vigilant. A definite integral is a, yes, product. What does it look like? It does look like the area under the curve, but it's not just the area. We'll find out next week why again, another reason it's so dangerous to equate definite integral with simple area. Okay, so stay tuned for next week. So we're going to use a Riemann sum. A Riemann sum is just going to be a more systematic way to use areas of shapes, so I can get away from counting. I don't have to count blocks. That seems a little slow. So I got a pool in the backyard. We're going to pump water into that pool, and I'm going to measure the rate at which water is pumped into this pool. And that is going to be measured in gallons per hour, and T is going to be measured in hours. So I got a table there of those values. So what's the meaning of the integral from 0 to 12 of W of t with respect to t? Well, again, a definite integral is representative of that's right, product. So we're going to multiply the units together. So we have gallons per hour multiplied by hours. Hours, hiya! Just gallons. The number of gallons that have been pumped into the pool over the first 12 hours is the meaning of that definite integral. Now, we want to estimate that value, but this time we want to do it with a Riemann sum. Just use some shapes. Don't feel like you've got to count blocks. So here is a quick graph of that information provided in the table. And I have no clue what the actual graph of W of t looks like. I've kind of drawn in a squiggly line there. The only data I know for certain are the red points that are in the table. I have no idea what happens in between. So we're only going to use this data that's given in the table. Can't make up any data. So in blue, you see the total interval, the interval from 0 all the way to 12. But the data is broken up into 2-hour sub-intervals. So that word sub-interval, you're going to hear it a lot in the coming lessons. So one option that I have would be to find the area, find the value of this definite integral by adding the areas of rectangles that are defined using the left edge of each subinterval. So the left edge of each subinterval, I only have, let's see, 1, 2, 3, 4, 5, 6 rectangles. So the 6 left heights, you can see a representative drawing there. And now I've got to multiply each of those heights by the base, because the area of a rectangle is the base times the height. So if I do 2 times the first left height, the first left height is the value of W at 0, then W at 2, 4, 6, 8, 10, but I'm not using the height at 12 because that's not a left height. So I've worked it out here on the side. Each of those subintervals is 2. So I've subbed in the data from the table, and I've got a grand total of 556 gallons. Now that's just an estimate. That's just really the only estimate I can have with the data that's given, unless I use the right side of each 2-hour subinterval. So now each 2-hour subinterval, the data that we're going to pull is from the right edge. So we're not using W at 0. Instead, we're using W at 2, 4, 6, 8, 10, and 12, those 6 heights. So each of those 6 heights multiplied by the base of 2 hours is going to give me an estimate of 682 gallons. I could also use trapezoids. And this looks like the type of Riemann sum that would most closely approximate a curve. So a trapezoidal area is 1/2 of the base multiplied by the sum of the 2 parallel sides. So I'm going to just apply that area formula 6 times. So you can see I've started at, since each base of the trapezoid is 2, I've got 1/2 times 2 times the sum of W of 0 and W of 2, and on and on and on and on and on we go. Do that 6 different times, subbing in the data from the table, and that gives me 619 gallons. So these are just 3 different types of Riemann sums that we could use. Rectangles on the right side, on the left side, or we could use a trapezoid to approximate the value of a definite integral. Again, just options that I have for Riemann sums. So we're going to see those 3 options plus one other one. Here's a picture of the 4 types of Riemann sums that we're going to use to turn a squiggly topped planar region into polygons, or polygonify a planar region. So we're going to have right rectangles, which I've spoken about, left rectangles, which I've spoken about, trapezoids, and then also midpoint rectangles. Now, midpoint rectangles, that's where we use the middle of each subinterval to define the height. So we have the base, which is the length of the subinterval. Then we're going to find the halfway point of that subinterval and use that to determine the height. So a quick little mnemonic device that I like for midpoint and trapezoids is the motto for midpoint rectangles should be find the height of the halves. So take the halfway point, then find the height, versus the trapezoids, which is find half of the heights, add 2 heights together, and then take half of that. So it's a matter of when we take the halfway point that is the deciding factor. Now, here's a little bogus thinking alert, and some of you guys are going to screw this up royally, is that when you do midpoint rectangles with a table of data, you can't just make up data that you don't have. This isn't science fair where you can just make up data that you don't have, okay? You can't make this stuff up. If I have a 2-hour subinterval, say from the pool data, The midpoint of the subinterval 0 to 2 is the 1 hour mark. Now, do I have data from the 1 hour mark? No. Can I make it up? No. Now, some of you might be thinking, well, yes, I can make it up. And this is how I made it up during my science fair project. I just took the 2 data points on either side and I found the halfway point in between. Doesn't that work? Not so fast. What did you just do? You just took the 2 heights and you found the halfway point between them. That, folks, is a trapezoidal approximation. You took half of the heights. You didn't find a halfway point and get one single height. You didn't understand that? Rewind it. Think about it again, because it does make a difference. If your midpoint Riemann sums and your trapezoidal Riemann sums are always coming out to be the same, it means you're doing one of them wrong. Okay? Now we'll take one last example and look at the different Riemann sums for this table of data. Now, it's nonsense what it represents. So we'll use the table of data for buffels per tandrip over the number of tandrips. And I've got a table of data for each tandrip, the value of how many buffels were perlified. So the subintervals in this table, you might notice, are unequal. That's okay. You don't have to have equal subintervals. It's nice to have equal subintervals because the evaluation is a little bit simpler. We can just factor out that common base. But you don't have to have a common base, especially with a table of data. So we're going to look at the meaning of this definite integral. Definite integral is a product. So let's take the x, which is tandrips. Let's take the y, which is buffels per tandrip. We'll multiply those two together and get, that's right, how many buffels were perlified between 2 and 12 tandrips? Of course. Now, how do we estimate that? Using a right Riemann sum. Here we go. So I've graphed that data, tandrips versus buffels per tandrip. And I've used the right end of each subinterval to define the height of a rectangle. I've kind of got them separate. I've got 4 different subintervals with 4 different heights. So to get the right Riemann sum, I'm going to do the first width multiplied by the first right height, which happens to be 7. So let me get the table of data up there again. So we have a width of 2 multiplied by 7, then a width of 1 multiplied by 9, a width of 3 on the next subinterval multiplied by a height of 6, and lastly a width of 4 multiplied by the right height, which is 2. And that's 49 buffels. Now the problem specified a right Riemann sum. And usually your problems will specify which Riemann sum to use. So what if I had said a left Riemann sum? A left Riemann sum would use the same widths, but we're going to use different heights, right? For a left Riemann sum, we're going to use the height that is on the left side of each subinterval. So that first subinterval from 2 to 4, I want the height that is on the left side. So the height at 2 tandrips. So that's 2, the base, multiplied by the height 11, and then so on and so on. You can see that here I've used the left heights, which would be an estimate of 80 buffels. But what if I had used a trapezoid? Again, I'm going to use the trapezoidal idea of 1/2 times the base times the sum of the 2 parallel sides. So you can see the math worked out. Let me get it around my head. Here we go. There is that math worked out for a trapezoidal approximation. Just finding the areas of 4 trapezoids. Boom, there we go. 64.5 buffels that were perlified. So you're going to be asked to do a certain type of Riemann sum. Left, right, trapezoid are your most common three, and then a midpoint is going to be a less common, but we'll definitely want to practice those in the problem sets. Again, midpoint, the difference is I find the halfway point on the subinterval and use the data at that midpoint to define the height of a rectangle. Last but not least, we want to be able to compare what a Riemann sum's value to a definite integral. So we're going to base that comparison on the behavior of the function. So if a function is decreasing, then any subinterval, if I define the height of a rectangle on the left side, then the left side is going to be greater. That rectangle that I draw is going to be a greater than what is the actual definite integral value. On the other hand, if the function is increasing on the same subinterval, if I use the left side, now that rectangle that I draw is too small. All right, so there is the old story of Goldilocks. Remember that one? Goldilocks says, no, this porridge is too hot. This porridge is too cold. This porridge is just right. Right? There are going to be some cases where Riemann sums are too big, and there are going to be other cases where the Riemann sum is too small. And there might be a case where the Riemann sum is just right. And just right in this case would be the exact value of a definite integral. You're going to be awfully lucky if you can get the Riemann sum to be the exact value. But we'll talk more about finding the exact value in a couple weeks' time. Be ready for that. That's going to be awesome. All right, so here is a table of information so that you can determine whether the given Riemann sum is bigger or smaller than the definite integral. Okay, so take a look at that. You might want to give that a second look. So overall, over these past two videos, we know that a definite integral is a product of x and y. We know that a Riemann sum can approximate the value of a definite integral just by adding up areas of familiar geometric shapes. We know that those geometric shapes include trapezoids and rectangles. And we know also how to overestimate and when Riemann sums over or under approximate the value based on the behavior of the function, increasing, decreasing, concave, up, or down. So that's what you need to know about definite integrals. Hope you learned something. And we're going to see whether you did when we get back in class. So I'll see you guys when I see you.